One more thing you may find interesting while we're up here is that that white kangaroo, the red tail and the white fuselage comes at a cost. In fact, 2 tonnes worth of paint to cover a 747. Now that weight represents 32 less people every flight. The wings of the 747-400 stretch 65 metres from wingtip to wingtip, and the 400 is identified by the winglet. This winglet helps direct the airflow over the wing. The curved surface on top of the wing makes the airflow faster, creating a lower pressure, whilst the flat surface on the bottom of the wing creates a higher pressure and the wing is pushed up. This is called lift. So the aircraft can fly at slower, safer speeds and still have lift, the wing is made bigger by extending the flaps and therefore almost doubling the overall surface of the wing. These are only used during takeoff and landing. If the aircraft flies at too low a speed, lift is no longer created and simply falls out of the sky as seen in this test situation. In aviation terms, this is referred to as the stall. Wings are also fitted with spoilers. These are designed to spoil the airflow over the wing and therefore spoil the lift. This provides for a more efficient descent and helps slow the aircraft on touchdown. Finally, if you're one of the many passengers who don't like the look of the wings flapping, they're actually designed to flex 13 feet or nearly 4 metres in rough conditions, with a safety margin of 2.5 times the normal operation.
Engine's being dropped out for a maintenance procedure where we've found a broken line between the engine and the firewall in the horizontal area of the strut. And to allow access, we're dropping the engine down so we can change the engine. These engines are Rolls-Royce RB211 524 G2s, and they produce approximately 57,000 pounds of thrust at takeoff on a standard day, which equates to about 20,000 shaft horsepower. This engine weighs approximately 9 tonnes, and we're about to drop it out into this cradle so we can actually work above it.
Even though these engines are huge and extremely powerful, their principle of operation is quite simple. The air is sucked into the front of the motor, it's compressed and exploded, and then blown out the back, creating thrust. The motor must perform over varying conditions, from sea level to minus 50 degrees at high altitude. Most of the parts inside the engine are designed to keep it going by supplying oil and fuel at the right temperature to the right place at the right time. This is all electronically controlled.
Each engine is inspected very regularly, approximately every 500 hours. We look under cowl for any damage. Any noted damage is rectified. Components are on a life cycle. They have a number of hours to run. Some components are on condition, like fuel filters. We pull those probably every 1,000 hours. I can't give you the exact figure. This component could even last the life of the engine before it's overhauled. But then again, it may fail and we've changed it in between.
So the life of the engine?
These have a life of around about 20,000 hours on the wing.
When you say life, up to 20,000 hours, is that it?
No, the engine's taken off the wing, taken our engine overhaul shop where it's split. The components that are damaged are replaced and repaired, and then the engine is reassembled, tested in the test cell and put back on wing.
And it can have a complete new life again?
It has a partial life. We don't actually do full overhauls, we do partial overhauls on the engines. There's components in the engine that deteriorate much more quickly than the rest of the engine.
Okie doke. Now one more thing, with the ignition, it starts, a jet engine starts by pouring fuel in and then it's ignited, I believe, like just a spark.
That's right. There's an igniter. You can't see it on this engine because it's inside. There's 2 igniters to the engine and they're only used to start the aircraft or start the engine, and then when it's in flight, it's continuous. The flame is continuous, it's there all the time.
So is it true it's like starting a gas stove? You turn on the gas and get a little clicker gun?
That's about right.
And away it goes. So when you hear the turbine spooling up, and then it's getting louder and louder, then all of a sudden it goes. That's when the ignition lights the fuel.
That's right.
And then the turbine's alight and stays alight.
Self-sustains and it keeps burning. The only time they put the ignition back on in flight is if they fly through icing conditions or through clouds.
That's when they refer to a flame out.
That's right.
So what an enormous amount of water or ice could actually put the flame out inside the turbine.
A sudden airflow reversal can put the flame out. So to protect against that, they leave the ignition on in those
igniter going.
Yes.
Testing of the jet engines is extreme. For thousands of hours, the engines are run under conditions such as this. A 1 in a billion chance rainstorm and crosswinds never experienced in real conditions. Now Greg, tell me this is normal.
That's normal, Paul. The idea behind it is to allow a little bit of flex on the blades, a little bit of movement, but by the same token, when the aircraft's at power, the blades move forward slightly in their mountings and become a solid disc.
When you say move forward, they actually pull forward?
They actually pull forward under thrust loads. During their testing, for certification on the aircraft, they are set up in test rigs. Birds of various weights are thrown at the fan blades or fired at the fan blades by air guns while the engine is operating at takeoff power to ensure that the aircraft can ingest the birds and continue flying. Also, they have a test where the aircraft engine is taken to takeoff power, an explosive charge is fired against one of the fan blades, and the engine has to maintain takeoff power for a certain period of time after that major structural damage that occurs.
Another engine in the 747-400 is the APU, or the Auxiliary Power Unit. This gas turbine engine is the noise you hear when the aircraft is stationary at airports. The APU provides pneumatic and electrical power to the aircraft when the main engines are not in operation. Even though small, this engine packs a power punch, supplying nearly 600 shaft horsepower.
These power units, there's 2 of them mounted on the aircraft, on the APU, and they're 90 kVA each. It's enough to power a very small city.
Now, before we get airborne, I should point out one more rather significant feature. The Boeing is made up of 6 million parts, 85 miles of hydraulic tubing, and 135 miles of electrical wiring, most of which is controlled from this room, every black box representing part of the Boeing's brain.
Well, good morning, fellas. Welcome to the briefing for the second of the Antarctic charters for this year's program.
This is the pilot's pre-flight briefing for our flight to Antarctica. Over the next 1.5 hours, every aspect of flying a 747-400 to the bottom of the world and back will be detailed. Hundreds of hours of flight planning, together with past knowledge, is combined as the final route decisions are made. 16 different alternatives are planned and discussed until the final decision is reached.
We're going to be operating in the area that comes around from Casey back around to Cape Washington. Cape Washington is about 150 miles north of the Scott Base and Mount Erebus. The ground along the coastline, as we'll discuss a bit later, is all fairly low, but over in this area here there is some quite significant terrain. Now, Australia is over where Ian is, so we're going to come down from roughly from where Ian is down into this area. Here's the pole, the magnetic pole, and of course the other pole is right back in the centre, and there's a geographic pole in about here as well.
En route requirements such as height and fuel are reinforced in the pilot's minds, including all safety and emergency procedures.